Okay, notes 4, sampling distribution of sample means. So first we're going to talk about the different notations. So we talked about sampling distribution of sample proportions, which is categorical data. And now we're talking about sampling distributions of sample means, which is quantitative data. So for parameters, remember we used P. For statistics, P hat. Sampling distribution mean is mu of P hat. And sampling distribution standard deviation is sigma of P hat. The next one, when we're talking about means, for a parameter, we're going to use mu and sigma. For statistics, we're going to use X bar and a capital S. For sampling distribution mean, we're going to talk about mu of X bar. And sampling distribution of standard deviation is going to be sigma of X bar. So we are changing up the notation a little bit, and that's because we're no longer talking about categorical data. We're now talking about quantitative data. Okay, so sampling distribution conditions for sample means. So we're still doing those three conditions, the random, independent, and normal. So random, as long as the sampling method is random, our mean is an unbiased estimator. Independent, when sampling, we have to make sure the 10% condition is satisfied. So that does not change. We're still doing the 10% condition, which is the sample size has to be less than or equal to 10% of the population size. For normal, however, we are no longer using large counts. Instead, we are using the central limit theorem, or CLT. So the central limit theorem states that when the sample size is sufficiently large, a sampling distribution of the mean of a random variable will be approximately normally distributed. So approximately normally distributed. The central limit theorem requires the sample values are independent of each other and that n is sufficiently large. Therefore, if the population distribution is normal, then so is the sampling distribution of X bar. This is true no matter what the sample size n is. If the population distribution is not normal or has an unknown shape, the central limit theorem tells us that the sampling distribution of X bar will be approximately normal in most cases as long as n is greater than or equal to 30. This is very important. So if the population distribution is not normal, CLT tells us that it will be approximately normal as long as n is greater than or equal to 30. So sampling distribution for a sample mean. Again, we want the shape to be approximately normal. Our center is going to be mu of X bar is equal to mu. And our spread is going to be sigma of X bar is equal to sigma divided by the square root of n. Okay, remember sigma of X bar and sigma are two different things here. Sigma of X bar talks about our standard deviation, and sigma is just a parameter that they give us in the problem. Okay. Again, these are only going to be true for approximately normal as long as the central limit theorem is met. So we can say if n is less than 30, then it follows a normal distribution. If n is greater than or equal to 30, then it will follow a normal distribution if central limit theorem is met. Okay. For the center, we know that the center is going to be mu of X bar equals mu as long as it's random, and that has to be random selection or random assignment. And then for the spread, we are going to meet the 10% condition just like before. So that's n is less than or equal to 10% of population size. And let me rephrase this a little. It should be by central limit theorem. Okay, so let's look at an example problem. So it says, suppose the heights of young women are normally distributed with mu equal to 64.5 and sigma equal to 2.5. Notice our parameters are given to us, mu and sigma. What is the probability that the mean height of an SRS of 10 young women is greater than 65 inches? So mu is equal to the average height of a young woman. And we're trying to find the probability that x bar is greater than or equal to 65. So we check each of the criteria. So random, well, they used an SRS, and that tells us that mu of x bar is equal to 64.5. Okay, independent, we're checking the 10% condition. So 10 is less than or equal to 10% of all young women, which is a safe assumption. So we'd say this is a safe assumption, which implies that sigma of x bar, which is equal to sigma over the square root of n, is equal to 2.5 over the square root of 10, which is 0.791. And then lastly, we have normal. And so remember, we're using the central limit theorem, okay, if applies. But since n is equal to 10, which is less than 30, this implies that the population distribution is approximately normal. Only when n is greater than or equal to 30, we say by the central limit theorem, the population distribution is assumed to be approximately normal. Okay, then we calculate. So we're trying to find the probability that x bar is greater than or equal to 65, where x bar follows a normal distribution. And I'm just going to move this so I can fit everything on one line, where mu is equal to 64.5 and sigma is equal to 0.791. Okay, so I am going to, let's see, split my view. I'm going to go to Desmos. Okay, and I'm going to add an inference, probability distribution normal, 64.5 and 0.791, create distribution. Click on the drop down. I want greater than or equal to, so that's the right region, 65. Okay, when I do that, I get the probability that x bar is greater than or equal to 65 is equal to 0.264. Okay, and I can go ahead and get out of that real quick, go back here, and go to my last step, which is to write the conclusion. So I would say the probability that the mean height of an SRS of 10 young women is greater than 65 inches is about 26.4%. Okay, let's look at another example. It says a particular restaurant that shall remain nameless is suspected of undercooking its burgers. The restaurant claims that its burgers are cooked to a medium doneness with an average internal temperature of 160 degrees Fahrenheit and a standard deviation of 5 degrees Fahrenheit. Here is our mu and our sigma. For the questions that follow, assume that the restaurant's claim is accurate and that the distribution of internal temperatures follows a normal distribution. So part A says, what is the probability that a single randomly selected burger is cooked to an internal temperature of 158 degrees or less? Okay. So we're not talking about a sampling distribution here, since we're only talking about one single randomly selected burger. This is very important, which means we can go straight into solving our answer. We do not have to prove the claims of random, independent, and normal. So we have the probability that x is less than or equal to 158, where x follows a normal distribution of mu equal to 160 and sigma equal to 5. Okay, so I would go ahead and open up my Desmos. Okay. I'm gonna just go up here and change these values. So I have 160, 5, and then less than or equal to, so that's left, 150. Did I type everything in correctly? Oh, 158. I wrote this wrong. This is supposed to be 158. Let's see, back 158. There we go. So I get that the probability of x being less than 158 degrees Fahrenheit is equal to 0.345. Okay, and that's my answer. Okay, which means if I was to write this in a sentence, I would say the probability that a single randomly selected burger is cooked to an internal temperature of 158 degrees or less is about 34.5%. Okay. Hi, baby. Okay, part B says a secret shopper comes in at random times throughout the day to test the internal temperature of the burgers. They select an SRS of 25 burgers and calculate the sample mean. What are the mean and standard deviation of the resulting sampling distribution? So I'm going to get out of this Desmos real quick so I have more space. Since this is talking about a sample mean, I know that I am looking at mu of x bar, which we know is mu, so that's 160. And then sigma of x bar is equal to sigma divided by the square root of n. Well, sigma is equal to 5, and we're taking an SRS of 25, so that's the square root of 25. So this is 5 over 5, which equals 1. Part C says the secret shopper in Part B obtains a sample mean of x bar equals 158. What is the probability that a random sample of 25 burgers produce a sample mean amount of 158 degrees or less? Assume all conditions are met. This is very important because if we're given this statement, we do not have to go through each of the conditions. We don't have to prove random, independent, or normal. They're saying they're all met. We can just continue and do the math. So what we're trying to find here is that the probability that x bar is less than or equal to 158, where where x bar follows a normal distribution of mu of x bar equal to 160 and sigma of x bar equal to 1. Okay, so I'm going to plug all those in, go back to my Desmos. Okay, I'm going to change this to be 160 and 1. And then less than or equal to 158, that didn't change, so I have my answer as 0.023. So the probability that x bar is less than or equal to 158 is equal to 0.023. What this means is that the probability that a random sample of 25 burgers produces a sample mean amount of 158 degrees or less is about 2.3%. So the last question says, why is there a difference between the results in A and the result in C? Explain why one is more likely to happen than the other. So remember, our result in A was the probability of a single burger of 158 degrees or less was about 34.5%. And then our random sample of 25 burgers produces a mean amount of 158 degrees or less is about 2.3%. So that's a big difference there. So in part A, we were looking at only the probability of a single burger. Since that distribution has more variability in it, we have a higher probability of it happening due to chance. So part A, we were looking at the probability of a single burger, which implies higher variability. Remember, the smaller the sample size, the higher the variability. Which means we have a higher chance of it happening. Okay. In part C, we're looking at the probability of 25 burgers. Since averages have less variability than individual values, we would expect a lower probability of that event happening. So in part C, we were looking at the probability of 25 burgers. This implies that averages have less variability than individual items, which means it's a lower probability of that event happening, which, man, I'm running out of room. I'm going to continue up here, which is a lower probability of that event happening. So think of it this way. If you were only looking for one object, so one burger, okay, you have a higher chance of that one burger meeting that criteria versus looking at 25 burgers and not saying out of those 25 which one meet the criteria, but taking all of the data for each of the 25 and taking the average. Okay, that's the big difference here. We took the average of all 25. Which means if we had some that had very high temperatures, some that had very low temperatures, it's going to mess up our average drastically. So in order to get an average temperature of 158, they would all have to be within the range of 158 degrees or less, which decreases our probability of that happening. So it's a lower chance of that happening versus of just picking up a single burger and seeing if that happens.